Hi there and welcome back to MA211. Today let's talk about transfer functions and zero state responses and zero input responses in the context of, well, we'll talk about second order constant coefficient, ODE. So let's think of a second order constant coefficient initial value problem, and this time I've used A, B, and C for the coefficients instead of M, C, and K. It doesn't really matter. So we've got this second order ODE, and it has a forcing term or an input term here. And we have some initial conditions, and I'm just doing this very, very generally, so I'm not going to specify what everything is. I'll just do it all in terms of these unknown coefficients, okay? So there are two problems that are related to this original problem that are worth mentioning. The zero input response to the system, I usually write that as y0i for zero input. It's a solution to the exact same problem. The coefficients are the same, but the forcing term is set to 0. Okay? So the coefficients are the same, the initial conditions are the same, but the forcing term is set to 0. Okay? So if you want to find the zero input response for a given system, you set the forcing term to 0, or the input term, you set that to 0, and you solve. Okay? The zero state response, you keep the forcing term here, that stays, but the initial conditions are set to 0, so these guys are gone. Okay? So these two guys, the zero state response, I usually write that as y0s for zero state. Okay? These two functions, y0s and y0i, they're related somehow to the solution to this initial value problem. They're not the solution to this initial value problem, they're solutions to related initial value problems. Okay? So if we take a look at this initial value problem, 3y double prime plus 2y prime plus 9y equals cosine 5t, and I want the initial values to be 6 and 11. The zero state response is a solution to this problem. Okay, so I would solve this problem and I would get y0s. It's zero state, so its initial state is all zeros. So these guys are zeros. Okay. And the zero input response is a solution to the problem with the exact same initial conditions, but with a zero input term. Okay? So again, zero state, zero input responses. These are fairly important in this context. Okay? So let's just try to take a look at what the zero input response to let's take a look at what the zero input response is, and we'll try and do it using Laplace transform. Okay? So, since the zero input response, right, the zero input response means you set the input term to 0. The zero input response will solve this initial condition, or this initial value problem. So, we'll Laplace transform everything in this problem. Right, so I have my a, and then I Laplace transform my y double prime, and I get an s squared. I've used capital Y0i to be the Laplace transform of the zero input response. Okay, so I'd get s squared times the Laplace transform of y minus sy0 minus y prime 0 plus blah 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 blah, just like always, right? And then I solve for the Laplace transform of the zero input response here. And I get this expression, something that involves the initial conditions and something that involves only parameters from the system on the bottom, okay? So this guy, the 1 over as squared plus bs plus c, that's called the transfer function of the system, right? And where did the as squared plus bs plus c come from? Where are the a, b's, and c's? Remember, this is the problem a y0 input double prime plus b y0 input prime plus c y0 input equals 0. Okay, so the a, b, and c in the transfer function, those come from the coefficients in the ODE. Okay, so this function is called the transfer function. It's a function of s. And your book writes it as capital W of S. So that's what we'll do. Okay. So the zero input response, the Laplace transform of the zero input response, is the transfer function times this thing, which depends on the initial conditions. And so if I inverse Laplace transform everything, the zero input response is the inverse Laplace transform of the transfer function times this thing, right? So if I wanted, I have the inverse Laplace transform of two things multiplied. I could write it as this is the inverse Laplace transform of the transfer function convolved with the inverse Laplace transform of this thing, ASY naught plus AY prime naught plus BY naught. Okay? And then this guy also has a special name. This is called the fundamental solution, but I don't think we'll talk about that this class. Just for your knowledge, this is called the fundamental solution, the inverse Laplace transform of the transfer function. Okay. So we've just written down the zero input response. You can think of it as it's the inverse Laplace transform of the transfer function times something involving the initial conditions. Okay, let's take a look at the zero state response, and we'll see if we can write down what it is also. Okay, so the zero state response is the original ODE, but it has zero initial conditions. So we'll Laplace transform everything, right? And since all the initial conditions are zero, when we Laplace transform everything, I would just get A times S squared capital Y plus BSY plus CY equals, and then I just have to write the Laplace transform of F, so that's capital F. Okay. And so then I would divide everything off, and I'd see that capital Y is 1 over AS squared plus BS plus C times F. Okay, and that's what I have here. So the Laplace transform of the zero state response is the transfer function again, right? 1 over AS squared plus BS plus C times the Laplace transform of the forcing function. Okay. And so if I inverse Laplace transform everything, the zero state response is the inverse Laplace transform of the transfer function times the fundamental solution. Okay, and again, I could, if I wanted, write this as this is the inverse Laplace transform of the transfer function convolved with the inverse Laplace transform of capital F, which is just little f. Okay, so if I wanted, I could do it that way, but we don't need to do that. Okay, great. So what good is all that? So let me go ahead and express the solution to the original system, right? So this is the original system that we started with. If I Laplace transformed everything and solved for capital Y, I would get this, okay? I'd have this thing and this thing on the right-hand side, and if you look, this thing is f of s times the transfer function, and this thing here is the initial conditions times the transfer function. Okay, and so I can inverse Laplace transform and get the inverse Laplace transform of f times w. Oops, and I forgot some terms here. This is the inverse Laplace transform of ASY naught plus AY naught prime plus BY naught times W of S. Right, it's just the inverse Laplace transform of this thing. Okay, and what is it? It's the zero state response plus the zero input response. Okay, so the crux of this is the solution to the initial value problem. It's the sum of the zero input response and the zero state response. Okay, let's think a minute about what's going on here. So the solution to the initial value problem, this is my initial value problem up here. Let me erase some stuff so that it's a little less cluttered. Okay? If you think of this in terms of a mass spring damper system, right, the solution to this thing is going to be, well, it's the motion that occurs when I release my object with these initial conditions and I subject it to this forcing term, okay? So there's really sort of two kinds of motion happening here. There's the motion that happens because you release the object from, or you release the object with these initial conditions, right? That's the motion that occurs because you displaced the object upwards and gave it some initial downwards velocity. There's the motion that occurs because of that. Then there's also motion that's occurring because you are subjecting the object to this external force. Okay? The zero input response is really the motion that's happening because of the initial conditions, right? It's saying, if I had just subjected the object to these initial conditions and didn't force anything, what would my displacement be? That's the zero input response. The zero state response is asking a different question. The zero state response is saying, what if I had applied the external forcing term, but I had just let the thing go from equilibrium? So it's saying, what's the motion that's in response to the forcing term? That's the zero state response. Okay? And what we're saying is that the motion that occurs due to forcing and initial conditions, or the solution to the initial, or the solution to the original problem, it's the sum of those two effects. It's the sum of the effect that's happening because of the initial conditions and the effect that's happening because of the forcing term. Okay? So that's what this is saying. The solution to the initial value problem is the sum of the zero input response and the zero state response. Okay, so let's take a look at an example. An example with a mass of an object with a mass of 1 kilogram is attached to a spring with a constant 34 newtons per meter. The environment offers 20 newtons of resistance when the object is moving at 2 meters per second. The object is released from an unknown position with an unknown velocity, and the resulting motion is this. Okay. Find the motion if the object is released from the same position and the same velocity, but it's subjected to an external force. Okay, so what do we want to do? We want to solve this ODE. We want to solve the ODE mass, so y double prime plus, what's my damping term? It's 20 newtons divided by 2, so 10y prime plus 34y equals sine 6t. So we want to know what happens when there is forcing and there is some initial condition, right? So y at 0 equals, I didn't tell you what the initial condition was, so we just have to write it in terms of these unknown guys, right? Y prime at 0 equals y naught prime. We'll write that, okay? So that's the problem we want to solve. Now, we have the solution to some different problem, right? It's like we performed an experiment and we released the object from an unknown position with an unknown velocity. So we released it from this position with this velocity, and we got this following motion. So when I say released, I mean there's no external forcing there. Okay? So we have the solution to this problem. Let me call it, I'll just call it Z, maybe. Or I'll call it Y, it doesn't matter. Y double prime plus 10y prime plus 34y equals 0. I told you that the solution to this problem with the same initial conditions is y equals 11e to the minus 5t sine 3t plus 14e to the minus 5t cosine 3t, okay? So I told you that's the solution. And what problem is this? This is the zero input problem, okay? So the zero input response is that guy. Okay. If I want to find the solution to the original problem and I have the zero input response, all I need is the zero state response. Okay? Need zero state response. Which is the solution to the exact same ODE but with zero initial conditions. So that's y double prime plus 10y prime plus 34y equals sine 6t. So you include the forcing term and you kill the initial conditions. Okay, and I've already solved that problem for us. So the zero state response is, I'm sorry this is ugly, but it's 26 over 901 e to the minus 5t sine 3t plus 15 over 901 e to the minus 5t cosine 3t minus 1 over 1802 sine 6t minus 15 over 901 cosine 6t. Okay. So we've got the zero input response. I found the zero state response. And by the way, when you're doing these problems, I'm assuming you know how to solve these. It's fine to just go ahead and use Maple. Yeah, the point here is, do you know about zero input and zero state responses? Okay. The solution to the initial value problem that we wanted, which is this guy, it's just the zero state response plus the zero input response. So the zero input response, again, it's this guy up here, and the zero state response is the one I just solved using Maple, and that's it. Alright, let's take a look at another example. So this time I have a mass with the exact same mass and damping coefficient and spring constant. The object is released from equilibrium position and it's subjected to a certain unknown force. Okay, and we get this this resulting motion. And I want you to find the resulting motion if we subject the thing to the exact same external force, but with these different initial conditions. Okay, so we move the thing down 5 units and we give it an upward initial velocity. Okay, so again, we want to solve this problem. Let's see, we want y double prime plus 10y prime plus 34y to be equal to this unknown external force. I didn't tell you what that is, but I did tell you that the initial conditions we want are 5 and y prime at 0 equals -3. And I told you the solution to a related problem. I told you that the solution to the same ODE, or oops, not the same ODE, the same left-hand side but with, oh no, same ODE. So I released the object from equilibrium position and I subjected it to a certain force, and I told you what the solution was. So I have the force and I released it from equilibrium position. So I told you what that is. This will be the zero state response. It is 11 cosine 7t plus 16 sine 7t plus 2e to the minus 5t sine 3t plus 3e to the minus 5t cosine 3t. Okay, so I gave you the zero state response. in order to find the solution of the problem, you'll need the zero input response. So let's do that. So we'll need the same ODE but with no input. So we'll need y double prime plus 10y prime plus 34y equals 0. We need y at 0 to be what? 5, and y prime at 0 to be -3. It's not an equal sign there. Alright, we can solve that problem using Maple. And if you do that, you get 28 over 3 e to the minus 5t sine 3t plus 5 e to the minus 5t cosine 3t. And so the solution to the original problem is this. It's just the zero input response plus the zero state response, and that's it. Okay. Let me kill off that thingy. Alright. Let's do one more. So I've got an object with an unknown mass. It's attached to a spring with an unknown spring constant, and the damping coefficient is unknown. The object is released from equilibrium and subjected to some certain force. Okay? The resulting motion is given by blah. So what's this guy? I released it from equilibrium and subjected it to an external force. So this is the zero state response here. In a separate experiment, I released the object from 1 meter above the equilibrium position with no initial velocity, and I didn't subject it to the external force. So no external force. This is the zero input response here. Find the resulting motion if the object is released 1 meter above the equilibrium position with no initial velocity and it's subjected to the force. So this guy is going to be, again, the sum of the zero input response plus the zero state response. And that's going to be these two added up. Okay, and that's it for transfer functions, zero input, and zero state responses.